This is an introduction to the lab where we measure E over m, or the charge to mass ratio for an electron. The learning outcomes for this lab are to further your understanding of the forces on moving charges and to improve your research skills by showing experimentally that E over m can be measured in a repeatable and accurate way. The lab objectives, and these are the three things that you will do in this lab, are to determine the direction of the current in the coil based on the circular path of the electron beam, then to make measurements to experimentally determine a value of E over m, and compare your result to the accepted value for E over m. The basic physics behind this comes from our electricity and magnetism introductory physics course, where we learned that a moving charge will experience a force in a magnetic and in an electric field, where the force in a magnetic field, F equals QV cross B, and an electric field is QE. The direction of the force in a magnetic field is given by the right-hand rule, as the picture on the right shows, where force equals V cross B, direction V cross B, but of course, remember to consider whether your charges are positive or negative when dealing with your directions. All right, so we have a force, QV cross B, which is making a particle go in a circle, making the electrons move in a circle. And we know when anything moves in a circle that there must be some force acting on it. Well, that centripetal force is the magnetic field force. So our centripetal force, mv squared over r, is equal to Fb, or the force on the electron in moving in the magnetic field. Connect those two to find the speed in terms of E, B, R, and M are the other variables. Remember that Q is the charge of an electron, E. Right, a charge like an electron that's accelerated across a potential difference V gets an energy E, where E is the charge of the electron. Let's look at this picture on the right. If we had a battery here, where this is the positive and this is the negative side, we accelerate our electron by applying a potential difference. Our electron is then pushed towards the other plate, and the total energy would be equal to the charge times the potential difference, or E times V. If that energy goes completely towards moving the electron, then it must be equal to the kinetic energy. So therefore, the kinetic energy, K, equals E times V. And the kinetic energy, we know from introductory physics, is equal to 1/2 mv squared. All right, so your challenge now is to combine all of those relationships and solve for E over m in terms of V, B, and R. The specifics of this experiment are that our magnetic field is generated at the center of these Helmholtz coils. And Helmholtz coils are such that they're relatively thin coils or narrow coils with a separation that's equal to the radius of the coils. And that gives you a uniform magnetic field at the center. Pretty cool. And you can get into it. The magnetic field at the center of a Helmholtz coil pair is mu naught Ni times r squared over r squared plus z squared to the 3/2. Feel free to look at your general physics too, or talk with me about this, or just enjoy it. But it'd be great if you actually work through where this comes from. The center of the coil arrangement has z equal r over 2, and so this whole thing reduces because now we've got everything in terms of r, and then it just becomes a number with some constants, mu naught n over r times I. In our particular coil, you can look this up, n equals 130 turns per coil, and the radius of the coils is 0.150 meters. So what you're going to find is that the magnetic field equals 7.79 times 10 to the minus 4 Tesla per amps times the current in the coils. That's really helpful, and you can use this as your conversion factor from current to magnetic field. So looking at the physics now, you've got your loops of current, your electrons, and then they are accelerated in a circle And you're going to determine what's the direction of the magnetic field and the direction of the current. Those are related, of course, in order to make those electrons turn in the direction that you see them turn in the lab. Right, so this video will describe the equipment that we're going to use for the E over M experiment. This allows you to measure this charge over mass ratio in a way where we get to use physics principles that we've learned already. So let's start with this unit here. This is the fundamental piece of equipment. These are our Helmholtz coils, which are separated by a distance equal to their radius. And in the center of that Helmholtz coils, we have our electron discharge tube. The tube has in it a heater, and when we heat up that heater, it emits electrons. The electrons are then accelerated by applying a voltage on opposite to one side of the heater. So we apply a voltage to the anode that accelerates the electrons, and as we increase that voltage, the electrons will go faster and faster because we're giving them more energy. Then we apply current to our coils, and that changes the magnetic field inside that tube. When the magnetic field increases, we remember that moving charges like electrons experience a force in a magnetic field, and so they change their direction. We watch that change, make some measurements, and use that in some great combinations of physics to determine this E over M ratio. So when you show up, you'll have to connect everything, but once you have it all connected, it's going to look something like this. And we'll step through how you're going to turn things on. Let's start with the most difficult piece, which is heating up the heater. The heater is being supplied on the left side of this box. This is going first to a variable resistor so that we can slowly decrease this resistance and therefore increase the amount of voltage that's dropping across the heater resistor. So we're going to start by turning this on. The heater now is getting some voltage across it. We'll increase that voltage by slowly adjusting this slider. And in the dark, you'll be able to see this much more clearly. Right now, you won't be able to see anything on the camera, and I can see a glow. I can see the glow right there, and as I move the slider, it will get brighter and brighter. And so I'll go to the maximum brightness. And now I have an electron source. So when it's dark, you'll now see the electrons coming out of that. Let's increase the voltage across the anode now. So we're going to do that by figuring out what's connected to what. We're going to increase the anode voltage with this supply. This will probably start off. You want to turn the DC voltage on. And then we're going to turn up the DC voltage, and we can watch the voltage with a multimeter. This helps you so that you can get an accurate reading of the voltage going to the anode. So I have here a multimeter that I'm using to measure the voltage across the anode. I'll turn that up to, as I'm watching, I'll turn it up to maybe 100, 200 in that range, and I'll see the electron beam. If I have no current going through the coils, the beam will just go directly down. So the next thing we want to turn up is the current going to the Helmholtz coils. And I've put in an ammeter so I can more easily measure. The current going from this power supply to the Helmholtz coils, which is what I'm going to use to figure out what the magnetic field is. So I'm going to turn this up. And I start seeing a voltage and a current displayed here, and a more accurate current to more significant figures displayed here. can go up to about 12 volts, and there will be the current will be much less than what it says on the box. All right, so now everything's on, and you are ready to take data by deciding what you're going to adjust and making measurements as you do that. Another tough thing is seeing the radius of your electron beam. You'll see that there are actually numbers, there are actually centimeters marked on the inside of the tube. So check that out, figure out how you want to light it so you can see the tube numbers or the radius numbers and see the electron beam. When you're done, of course, just turn down all of the knobs first before turning off the voltages. Decrease the current or the voltage across to the heater. And that's it. These are the pre-lab questions, which are in the lab information sheet. And you want to answer all of these questions in your lab notebook, in your pre-lab section of your lab notebook. But the ones called forum, post them in the preparation forum so we can discuss them before lab. And you're ready to go.